Hello, everyone. Today we continue with non-homogeneous linear equations. The other day we talked about two different techniques to solve non-homogeneous linear equations. One was undetermined coefficients, which we talked about them. The other was the variation principle, which I started talking about them, but we didn't get to a satisfactory point. So I'm going to talk about variation principle, and then hopefully today we can finish chapter 0 and start chapter 1. Okay, and hopefully we can start chapter 1, and we will talk about Fourier series and different kind of convergence for functions. Okay. Okay, aside from variation principle, which I'm going to talk about it now, is there any question from the previous meeting? Okay, if not, I would start. If you have any question from yesterday, you can ask. Okay, so we talked about this variation principle. So let me remind you what this thing is. Suppose we have a second order linear ordinary differential equation, which is non-homogeneous. So it would be something like this: the second derivative of y with respect to x plus some function times derivative of y with respect to x plus another function is equal to f of x. It is, suppose it is non-homogeneous in the sense that f of x is not the constant function 0. It's a non-zero function, right? And then we want to find, and the goal is to find, we are looking for the general solution to this equation. So the idea is to find this general solution in 2 steps. The idea is to look for a general solution. We break it into 2 parts. First, we find the general solution to the homogeneous part. And then we look for so-called a particular solution. This particular solution is a solution for the non-homogeneous part. There are different ways to do that. So this variation principle is what we are going to do now. Let's start with an example, and then I would explain the general idea behind what we are doing. So it might, as I mentioned the other time, this technique might look a little bit strange. It might get a little bit to get used to it. So suppose we start with an equation like this: the second derivative of y with respect to x plus y, suppose it is equal to 1. So using, well, if we want to solve this equation, first I should find the solution to the homogeneous part. So the first step would be looking at the homogeneous equation, which corresponds to this one. And that equation would be the second derivative of y with respect to x plus y is equal to 0. So it means, well, if I want to write it a little bit in more simpler terms, so it means the second derivative of y is equal to minus y. And as I mentioned the other time, we know two functions with this property. One of them is sine of x, and the other one is cosine of x. Because it is a second order linear differential equation, we would expect to have two independent solutions. And here we have it. We have two linearly independent solutions, sine and cosine. So the general solution to the homogeneous part would be a linear combination of sine and cosine. Now we want to look for the solution to the non-homogeneous part. So we are looking for so-called a particular solution. As I mentioned the other times, sometimes we might simply be able to guess. So here it's not hard to see the constant function 1 is a particular solution, right? The derivative of the constant function is 0, and if I let y to be equal to 1, it certainly satisfies the equation. The second derivative of constant function y with respect to x is 0. And if I just add it to the constant function y, it would be equal to 1. So it does satisfy the equation. So the general solution would be the general solution to the homogeneous part plus this particular solution. But now let us use this variation principle. Suppose at some point we can't guess. Suppose here we guessed this is a particular solution. It is correct that in this example it's very simple, it's easy to guess. But suppose we don't want to guess. We want to find a way which works in other cases too. So I want to tell you about a method to find this particular solution, a particular solution, rather than guessing that. So keep the solution up to here, keep the homogeneous solution. We want to find another way to, we're looking for another way to find the particular solution. So the variation principle says, suppose the particular solution can be written as this. So take your general solution to the homogeneous part, which are cosine and sine. Suppose we can multiply these functions with two other functions. Let's call them u1 of x and u2 of x. And suppose there is a solution, a particular solution to the equation which has this form. For two unknown functions, u1 and u2. And now here, the goal is to find u1 and u2. We want to find what are these functions. So we would assume there is a particular solution like this, and then we would try to solve the equation for u1 and u2 to see if there are such functions or not. Okay. Great. Now, so the point is that if this is a particular solution, it should satisfy the equation, right? So if yp is a particular solution, we should have the second derivative of yp plus yp should be equal to 1. What is the second derivative of yp? Let's compute these things. So the derivative of yp is equal to, well, u1 prime cosine of x minus u1 sine of x plus u2 prime sine of x plus u2 cosine of x. That's the first derivative. And now we should compute the second derivative. It would be equal to the second derivative of u1 cosine of x minus derivative of u1 sine of x minus u1 prime sine of x minus u1 cosine of x plus u2 double prime sine of x plus u2 prime cosine of x plus u2 prime cosine of x minus u2 sine of x. Now I can plug in these two into the equation. I can plug in the second derivative here, and I can plug in the y itself here, and let their sum to be equal to 1, and see what kind of equation I would get for u1 and u2. And hopefully I can solve that to find u1 and u2. Okay. So the sum of what we have here, well, we should add the second derivative of y to y itself. So I should add what I have here. I should add it to what I have here. And their sum, the left-hand side, would be, let's see if anything cancels out. Yes. So this u1 cosine would cancel this minus u1 cosine. And this u2 sine would cancel this u2 sine. So their sum is equal to u1 prime cosine of x minus u1 sine of x plus the rest. Let me just write it down. This can be, we can simplify this a little bit. It would become equal to, well, what do we have here? It would be equal to the second derivative of u1 cosine of x plus the second derivative of u2 sine of x. And then we have minus 2 times u1 prime sine of x plus u2 prime cosine of x. And we want that to be equal to the right-hand side of our equation, which is simply 1. So this is the equation we want to solve to find u1 and u2. So as I mentioned the other day, this equation looks complicated. Well, we should think how we can solve this equation. So the idea is that here we have one equation plus should be minus, thank you. Okay, so the idea is that we have one equation and two unknowns. So usually when we have one equation and two unknowns, you might expect to have many solutions. I would not go into explaining what it exactly means. There is a theory to explain that. It's called the elliptic theory of partial differential equations, but I don't want, well, here we have ODE, but anyway, I do not want to get into that. But usually one idea to kind of go around this problem and do something that we can find some specific U1 and U2 is to add an extra equation, right? To add an extra requirement, okay? So here, one extra requirement we can add is we can assume that something is 0 here. So maybe I would assume that, for example, what we have here in this parentheses is equal to 0. And then this part is equal to 1. That's one assumption we can have. For example, if this part is equal to 0, the other part is equal to 1. So, but the idea is that the question is that how can we be sure this kind of the requirement we are adding, the thing we are assuming is the correct one. Maybe our assumption is not the correct assumption, right? How can we be sure to find the correct assumption? So there is one standard one which works and is the good one. So I would write that in more general case now here. So in more generally, so we would have our second degree equation. It would be a function here times du dx plus another function x times y equals 0. And so the idea is that suppose we have looked at the, so what was the first step? The first step was to look at the homogeneous part of the equation, which in general case, it would be this thing. Suppose we have some non-homogeneous part too. Sorry, let's call that f of x, the non-homogeneous part. And we would first look at the homogeneous part, and then we would find two solutions because it's a second degree equation. Let's say we would find two solutions here, and we call them y1 and y2 of x. And the variation principle says, let's assume the particular solution is something, another function, say v1 times y1 plus v2 times y2. Now, if we just plug in this thing into the equation, into our equation, what we would get is very similar to what we had in the previous page. So more generally, if I plug this, so I should compute this derivative of this thing, which would be something, and then the second derivative of this thing, which would be something, and I would plug in all these three into this equation. I would plug in the second derivative of y, the derivative of y, and y itself. And I would let that to be equal to f of x. And I hope to be able to solve it to find v1 and v2. These are the unknowns here. The equation we would get is this one. So let me just write down the equation we have. v1 prime, y1 prime plus v2 prime, y2 prime plus v1, y1 second derivative plus k, y1 plus p, y1 plus v2, y2 prime plus k, y2 prime plus p y2 equals f. This is the result of just plugging in the y prime, the second derivative of y, and y itself into the original equation. Now remember, we were assuming y1 and y2 are the solutions to the homogeneous part. Therefore, y1 and y2 both satisfy this equation, right? They are solutions to the homogeneous part. And therefore, what I have here would be 0, and what I have here would be 0. So I would end up with this thing, y1 prime, v1 prime, y1 prime, plus v2 prime, y2 prime would be equal to f. Okay. Now, so this is the equation we would get to. And as you can see, again, we have one equation and two unknowns. So in general, the second equation, so as I told you, we want to add an extra equation. We just add that. The extra equation we would add, and we hope it would be a good one, is this one. v1 prime y1 plus v2 prime y2 equal 0. If we just simply add this extra requirement, we would get two equations and two unknowns. And we can hope we would be able to solve this thing. There is a reason that this equation, adding this equation, makes sense. So let's see why it makes sense to add this equation. So this is the equation that we would simply get by plugging in the thing we had for y into the equation. And this is the thing we just simply add ourselves. So the point is that here we have two equations and two unknowns. But the unknowns you have here are v1 prime and v2 prime. So simply we can solve this thing, thinking about it as a system of linear equations. We can solve this one to find v1 prime and v2 prime, right? For example, I can multiply the first equation by y1, and I can multiply the second equation by y1 prime, right? What would I get? I would get v1 prime y1 prime y1 plus v2 prime y2 prime y1 equals f y1. And then the second equation, if I multiply it by y1 prime, it would be v1 prime y1 prime plus v2 prime y2 y1 prime equals 0. So if I subtract the first equation from the second equation, these two would cancel. And we can factor v2, so we would get v2 prime times y2 prime by 1 minus y2 y1 prime equals f y1. Therefore, v2 prime is equal to f y1 over y2 prime y1 minus y2 y1 prime. Therefore, you can find v2 by integrating what we have on the right-hand side. Similarly, we could compute the y1 too, right? We could solve the equation to find v1. If we can compute these integrals, if we are able to compute these integrals, the particular solution would be v1 times y1 plus v2 times y2. And that would be our solution. Now, going back to the question, so now with this understanding, we can go back to this equation we had, the second derivative of y with respect to x plus y equals 1. So here y1 and y2 are cosine of x and sine of x, right? This extra equation which we add was v1 prime y1, which is cosine of x, plus v2 prime y2, which is sine of x, equals 0. That's the extra equation. The equation which simply follows from our computations would be this one. What would it be here? It would be minus v1 prime sine of x plus v2 prime cosine of x equals to 1. And now we should solve this thing to find v1 and v2. First, we would find v1 prime and v2 prime, and then we would integrate to find v1 and v2, right? Let's see here if we can do that. So here, yeah, so here I would multiply the first equation. I would multiply the first equation by, I would multiply the first equation by sine. So I would get v1 prime sine of x cosine of x plus v2 prime sine of x squared equals 0. And I would multiply the second equation by cosine. So v1 prime sine of x cosine of x plus v2 prime cosine of x squared is equal to cosine of x. Now, if we subtract these two equations, or add them actually, if we add these two equations to each other, we see v2 prime times sine squared of x plus cosine squared of x, which is actually equal to 1, is equal to cosine of x. So v2 prime is equal to cosine of x. So v2 would be integral of cosine of x dx, which is just sine of x plus a constant. I think I can take this constant to be 0 now because I'm looking for one particular solution. I'm not looking for all solutions. So v2 is equal to sine of x. Now I can plug that actually into this equation to find v1. So v2 prime would be cosine, therefore v1 prime sine of x plus cosine squared of x is equal to 1. Therefore v1 prime would be cosine squared of x minus 1 over sine of x, I think. If that's correct, yes. So cosine squared minus 1 is minus sine squared of x, and the result of this division is just minus sine of x. Therefore, v1 is integral of minus sine of x, which would be cosine of x. Plus a constant here, I would again take the constant to be 0. So v1 is equal to cosine of x. v2 would be equal to sine of x. And the particular solution was supposed to be v1 y1 plus v2 y2. Remember, y1 and y2 were cosine and sine. So here would be cosine times cosine, which would be cosine squared, plus sine times sine, which would be sine squared, and that would be 1. So the particular solution is just 1, which of course we could guess the particular solution to this equation is 1. If you let y to be equal to 1, of course that would work. That would be a solution to this equation. But this was a more complicated way to find the same thing that we could guess. But the point here is that if this 1 is any function f, this method should work, at least in good cases. The only point is that here, when you want to take this integral in the last step to find V1 and V2. First, you would find V2 prime or V1 prime, and then you should take an integral. Computing this integral might be complicated. So assuming we can take the integral, we would be able to solve the non-homogeneous equations if we can solve the homogeneous one. Okay, is there any question here?
Any tips for discerning which of the two methods that we've learned so far?
Yeah, so my suggestion would be always first look at the equation to see if you can guess what is the particular solution. So here, if you look at the equation, you would get the solution, you would guess the solution is 1, right? So you don't need to go into this complicated method, not very complicated, but it's not also trivial, to a long computation to do that. So the first suggestion would be just try to guess. The second suggestion would be use undetermined coefficients. That was easier, because there you were supposed to find some constants, right? A1, A2, etc. And finding constants and solving a linear system of equation is a lot easier than solving integrals. If these two techniques don't work, then you should consider this variation principle. Also, I see a question in chat. Should the plus inside the parentheses be a minus? Is it from now or from before? I think it's from before. Okay. I think I corrected that.
Thank you.
Yeah, sure. Okay, so that's that. So now I want to continue to go to chapter 1, which is about Fourier series and integrals. So we want to start a new chapter. We will come back to chapter 0 whenever it is necessary. Okay, so let's start with Fourier series and integrals. So this section is quite important because we use Fourier series a lot to kind of solve our equation. This is one of the main topics we use in this course. Okay, so the main object of study here are periodic functions. So I'm assuming you are familiar with the definition of a periodic function. So maybe it would be good if I just do a little review of the concept. So we say a function, say f, defined on some subset of R. Well, let's say it's defined on some a subset of R. To R, we say this function is a periodic function if there exists some number, let's say some positive real number, such that f of x plus p is equal to f of x for any x in the domain of this function. Okay, so whenever we have this, whenever f of x is equal to f of x plus p, well, because this is correct for any x, x plus p itself can be the x, the input. So this is supposed to be equal to f of x plus p, which is plus 2p, etc. Also, it is equal to f of x minus p. So in some sense, the domain of periodic functions it goes to plus and minus infinity. Now, usually well, at least in this course, the period of function f, we usually mean the smallest positive number, p, such that it has this property, such that f of x plus p is equal to f of x for any x in the domain. So the most well-known examples of these functions are, of course, sine and cosine and tangent, the trigonometric functions. So I would just remind you, so if we look at this function, y equals a sine of, say, bx plus c, the period of this function is equal to 2 pi over the absolute value of b. So if we multiply x by a number, we would divide the 2 pi by that, and that would be period. The same is correct for cosine. The period of a cosine of bx plus c is also the same thing. If the function sine here is, if we raise it to some odd number, the period does not change. It is still equal to 2 pi over absolute value of b. But if we raise that to some even number, what happens is that the period will become pi over absolute value of b. We would divide 2 pi by 2. Also, for example, the absolute value of sine of bx plus c has the same property. The period is pi over absolute value of b. Actually, the same thing is even also correct for tangent. The tangent of bx plus c, again, is pi over absolute value of b, not 2 pi. It's still pi. Let's start with the concept of Fourier series for periodic functions. So the idea is to express a periodic function as a sum of trigonometric functions. So suppose we have a function f of x, y equals to f of x. Let's assume that f of x is a periodic function, and suppose the period of f is equal to exactly 2 pi, right? So in that case, when we are looking at, for example, the graph of the function f, we only need to look at the graph from minus pi to pi, right? Because the length of this interval is 2 pi, and everything else would be repetitive. So if the function looks like this on this interval, it's just going to continue this behavior everywhere. Okay, suppose the function f has this property. Now, there is another function which has the same period as this function, and that's this one. So suppose, think about sine and cosine, say sine of x. This function is another function which its period is 2 pi. Same thing is correct for cosine of x, right? Now, if we look at sine of, say, 2x and cosine of 2x, the period of these two functions is 2 pi over 2, which is pi. But if we think about the linear combination of all of these functions, the period of all this linear combination is still 2 pi. If I add other trigonometric functions, say e sine of nx or f cosine of mx, and even if I add a constant, let's show that with capital C, the resulting function, this function, still has period equal to 2 pi, okay? And the point is that here I can continue this sum to infinity to get a series. Now the question is that what is the space of functions I can construct with this trigonometric function? In another language, if I let this sum to go to infinity to get something like this, a constant plus sigma an cosine of nx, and goes from 1 to infinity, plus sigma bn sine of nx, and goes from 1 to infinity. If I have a function with period 2 pi, can I choose these constants a0, an, and bn such that I would get this equality? Is that possible or not? So, for example, let's say f of x is equal to the function x for any x between pi and minus pi. So it looks like this. Okay, and then suppose I would repeat this function because I want to assume it's periodic. I would repeat just the same graph over and over again. I would get a periodic function, which is not even continuous, right? So the question, for example, here is that can I choose these numbers, constants, a0, an, and bn, such that this sum would be equal to 1? Is that possible or not? That's the main question of the Fourier series. Now, the way we solve this one is by assuming we can, and we would see where it would take us. So suppose it is possible. So suppose f is a periodic function with period 2 pi. Suppose I can find a0 and an and bn such that this equality holds. I want to assume this is correct. And then I want to kind of try to manipulate this one to find these constants, an, bn, and a0. Okay. So what I would do is I would take integral of this equation. So I would integrate both sides from minus pi to pi. So would be minus pi to pi. I can just combine these two sums. So it would be an cosine of nx plus bn sine of nx. Okay, so now there are things here that we know what is the result of some of these integrals. So for example, here, the integral of a0 from minus pi to pi dx is equal to a0 x from pi to minus pi, which is simply 2 pi a0, right? So that's the value of this integral. What about the rest of them? So I can extend these integrals. So the second sum has some integrals of this form. Integral of an cosine of nx dx, and it has some integrals of the form bn sine of nx dx. Okay, but the interesting thing is that the integral of, well, let's first look at sine. What is the integral of bn sine of nx dx from minus pi to pi? Well, bn is a constant, so it just comes out of the integral. Right? And the integral of sine of x is minus cosine of x So we guess the integral should be something like cosine of nx. Well, actually, it is the same thing, just divided by n from pi to minus pi. So if we plug in pi and minus pi into cosine, both of them are 0. So the result would be 0. So it doesn't matter what n is, well, as long as n is non-zero, because we're dividing by 0 here. It is non-zero. Actually, the sum starts from 1. So these integrals, all of them, are equal to 0. Completely in a similar way, these integrals are also equal to 0. Sorry, the integrals, not the terms themselves. These integrals. So these integrals, both of them become 0. So this equation reduces to integral of f of x dx from minus pi to pi is equal to 2 pi a naught. So here we have it. We have the value of a naught. A naught is equal to 1 over 2 pi integral of f of x dx from minus pi to pi. That's the value of the 0 term, the constant a naught. Now we want to look for the other terms, right? Is there any question up to this point? Let me look at the chat. Any question here? Okay. So let's continue. So now that I have this thing, so now I know f of x is equal to a naught, which is 1 over 2 pi integral of fx dx from minus pi to pi. The whole thing, remember, is just a naught plus sigma an cosine of nx plus sigma bn sine of nx, and goes from 1 to infinity. Now here I want to look for an and bn, right? I want to find an and bn. How can I do that? So the idea is that now I can multiply the whole equation by something like sine of, well, here I chose the variable n. I can multiply everything. So multiply everything by, say, sine of mx. So what are we going to get? So on the left side, we would have f of x times sine of mx. On the right-hand side, let me still show it with a naught times sine of mx plus sigma an cosine of nx sine of mx. N goes from 1 to infinity. N is what is changing, m is constant, plus sigma bn sine of nx sine of mx. N goes from 1 to infinity. That would be the first step. Now the second step would be integrating this thing. So integrate what we have here, take integral of this thing, again from minus pi to pi. There would be dx here, and take integral of this thing from minus pi to pi, and integral of this thing from minus pi to pi dx. Okay. So again, we know the value of some of these integrals. For example, again here, we have integral of a constant times sine of mx. And we just saw integral of sine of nx or mx, doesn't matter, is 0. So that this integral would be 0. What about the other integrals? We have two kinds of integrals here. One sort of integrals are of the form integral cosine of nx, sine of mx from minus pi to pi dx. And then the other sort of integral is sine of nx, cosine of mx dx from minus pi to pi. So the good thing is that these integrals are easy to compute. So for example, the first integral is always 0. Integral of cosine of nx, sine of mx from minus pi to pi is always 0. So going back to our equation, and that means these terms, all of them are equal to 0. What about sine of nx? Oh, sorry, the second one, I repeated the same thing. So the second one should be sine of nx, sine of mx. What about the second one? Well, the interesting theory is that it's almost always 0, the result of this integral. There's just one special case, which the value of this integral is non-zero. And that's when n and m are equal. So at the moment that these two numbers are equal, this integral is actually equals to pi. That's interesting because if we look at the integrals we have here, we have a sum here, and it's a sum over n, right? N is equal to 1, 2. At some point, n becomes equal to m. Before that moment, all of the integrals are 0. At the exact moment where n is equal to m, this integral is equal to pi. After that, when n becomes equal to m plus 1, m plus 2, etc., after n is larger than m, these integrals again are 0. So this sum, all of the terms are 0, just one term which is equal to pi. So also we have, note that there is also a coefficient bn here. So it would be pi times bn. Okay. So the equation we would get is, on the left hand side, we had integral of f of x, sine of mx, dx from minus pi to pi. On the right hand side, we had a lot of zeros, and the only non-zero term was bm pi. Therefore, bm is equal to 1 over pi integral from minus pi to pi fx sine of mx dx. So that gives us the coefficient bn here. We could compute the coefficients an here too in a similar way. Rather than multiplying everything by sine of mx, we could multiply everything by cosine of mx, and we would get very, very similar thing. So if I want to write down the result, the function f of x can be written as, well, if it can be written actually. If we can write it as a naught plus the sum sigma n from 1 to infinity an cosine of nx plus sigma n goes from 1 to infinity bn sine of nx. Then we can compute these values a naught, a1, an, and bn. So a naught would be 1 over 2 pi. Note that this is the only one which has the constant 2 here. The rest of them are 1 over pi. Integral from minus pi to pi fx dx. An is equal to 1 over pi integral from minus pi to pi fx cosine of mx nx dx, and bn is equal to 1 over pi integral from minus pi to pi fx sine of nx dx. Note that an is the coefficient of cosine, and also in its definition you would see cosine here. Bn is the coefficient of sine, and also in its integral you would also see sine. Maybe that would be useful to memorize these formulae. So we have these formulas. Maybe we can try a few examples, right? So let's do an example. So suppose we have a function fx. Suppose we are only considering this function. Suppose it is equal to x, the function y equals to x. Suppose it's only defined on the interval from minus pi to pi. Okay, from minus pi to pi. And we want to write down the Fourier series for this one. So the question is find a0, an, and bn. What are these constants? Okay, think about this one for maybe 5 minutes. Compute these integrals, and then I would solve it. Okay. So let me write down the answer. So we have a0, its definition was 1 over 2 pi integral from minus pi to pi fx dx, which is 1 over 2 pi integral of x dx from minus pi over pi. We don't even need to compute that, right? Integral means the area under the graph of a function, which is here. And as we can see, this negative part and this positive part, they cancel each other. So this integral is equal to 0. Now, the other part is an, which is 1 over pi integral from minus pi to pi fx cosine of x nx dx. Actually, this integral we also don't need to compute, but I would just ignore that for a moment and I would just compute the integral. So the integral would be integral of x cosine of nx dx, right? And if I want to compute this integral, what should I do if I want to compute this integral? So there are two ways to do this one. One way is doing integration by parts. The other way is noticing that what we have inside integral, x cosine of nx, if we change x to minus x, if I replace x with minus x, I would get minus x cosine of minus nx, which is equal to minus x cosine of nx. So if I change x to minus x, the integrand inside integral becomes negative, right? These functions are called these functions are called odd functions. And when we have an integral of an odd function on a symmetric interval, goes from, for example, 0 to pi and from 0 to minus pi, the graph would be again something like this. So for example, if it looks like that on the positive side, it would look exactly the same on the negative side, but it would be just negative of that. And again, this negative area and this positive area cancel each other. So understanding this is an odd function tells us this integral is also equal to 0. Okay, so the only remaining part is Bn. Bn is equal to 1 over pi integral from minus pi to pi fx sine of nx dx, which here it would be 1 over pi integral from minus pi to pi sine of x sine of nx dx. Okay, so here I want to do integration by parts. Remember, integral of u dv is equal to uv minus integral of v du. So here I want to take u to be equal to x and dv to be equal to sine of nx dx. So du is going to be equal to dx, right? And v is going to be equal to minus cosine of nx over n. Now, having this integration by part formula in mind, Bn would be equal to 1 over pi uv, which here would be minus x cosine of nx over n minus integral of v, which is minus cosine of nx over n du, which is just dx. This minus sign here and this minus sign there, they cancel each other. So I would simply write plus this integral. And this integration, we should do this integration from minus pi to pi. Now, in order to complete this integration, I should just compute this part. This over n, 1 over n comes out of integral, and integral of cosine of nx is sine of nx over n. I have 1 over n already, so it would be sine of nx over n squared. Therefore, Bn would be equal to 1 over pi sine of nx over n squared minus x cosine of nx over n from pi to minus pi, which would be equal to 1 over pi sine of n pi over n. So what is, let's write it here, what is sine of n pi? Well, sine of 0 is 0, sine of pi, 2 pi, 3 pi, everything, all of them are equal to 0. So this part would be 0. Minus pi cosine of n pi. What is cosine of n pi? Well, cosine of 0 is 1, cosine of pi is minus 1, cosine of 2 pi again is 1, so it's minus 1 to the power n plus 1, right? Or minus 1 to the n, actually. So it would be minus pi times minus 1 to the power n over n. And then we should plug in minus pi into this solution. So again, we would get 0 minus pi would be pi over n times cosine of minus n pi, which would be again minus 1 to the n. So the result would be 1 over pi and minus 2 pi minus 1 to the n, I guess. So pi and pi, they would cancel each other. This minus 1 would adds up there, it would be 2 over, sorry, there is also n here, over n. 2 over n minus 1 to the n plus 1. So that's the coefficient. So if you write x as that sum, a naught, the first term would be 0. The coefficients of cosine nx would also be 0. The only non-zero parts are related to the parts related to sine of nx. So we would get sigma bn sine of nx, which is 2 over n minus 1 to the n plus 1 sine of nx. And goes from 1 to infinity. So that would be the Fourier series of x. Is there any question? Okay. Okay, great. So let's compute some examples. You can think about each one for a few minutes and then I would solve them. So find the Fourier series for the function f of x. Suppose f of x is equal to, let's say, minus 1 for x from minus pi to 0, and is equal to 2 for x between 0 and pi. Find the Fourier series for this function. Okay. If there's no answer, I can start writing. Does anyone have the answer? Okay, so let me write down. So again, we would start with a naught. It is supposed to be 1 over 2 pi, integral from minus pi to 2 pi fx dx. In this case, it's obvious that we can break the integral into two parts, from minus pi to 0, and then the integral from 0 to pi. From minus pi to 0, the function f is equal to minus 1. From 0 to pi, the function is equal to 2. So the result would be, well, the first integral is just minus x, and the second integral is just 2. Sorry. The second integral is just 2x. So the first integral would be equal to minus pi, and the second integral would be equal to 2 pi. And the sum would be pi over 2 pi, which is 1 over 2. So that would be the value for a naught. Therefore, a naught is equal to 1 over 2. Now we should compute an. An is supposed to be integral of 1 over pi. Integral from, well, again, we break it into two parts. We would have one integral from minus pi to 0 and one integral from 0 to pi. And we should have cosine of nx times fx. So f in the first part is minus 1. So we would have cosine of nx dx. And in the second part, f would be equal to 2. So we would have 2 cosine of nx dx, which is equal to 1 over pi. Well, minus 1 comes out of integral. the integral of cosine is equal to sine. Integral of cosine nx is sine nx over n. And then we have from minus pi to 0. Again, 2 comes out of integral. Integral of cosine nx again is sine of nx over n from 0 to pi this time. So if n is equal, so if x is equal to pi or x is equal to 0 in both cases, sine or even pi, in all cases, sine would be equal to 0. So the result would be equal to 0. Yeah. Therefore, this is an, actually. Therefore, an is equal to 0. Now we should compute bn, and bn is equal to 1 over pi, again integral from minus pi to 0, f of x, which is minus 1, this times sine of nx dx. And then integral from 0 to pi, 2 times sine of nx dx. It is equal to 1 over pi, minus 1 comes out of integral. Integral of sine nx is minus cosine nx over n. We should evaluate that at minus pi and 0. Minus 2 times 2 minus cosine of nx over n from 0 to pi. This is equal to 1 over pi times, well, these minus 1 and minus 1, they would cancel each other. It would be cosine of 0, which is 1 minus cosine of n pi over n. And cosine of n pi is equal to minus 1 to the n. So that would be the result for the first part. Yeah, I think we don't have over n here. I brought that out of the parentheses. So we do 1 minus minus 1 to the n plus 2 over n times, if again n is if x is equal to pi, we have cosine of n pi. Again, it is equal to minus 1 to the n, minus if x is 0, we would have the cosine of 0 is 1, so we do minus 1, which is plus 1. And therefore, it is equal to 1 over n pi, 1 minus minus 1 to the n, plus 2 minus 2 times minus 1 to the n, and it's equal to 3 minus 3 times minus 1 to the n. Yes. So the function f of x we had, f of x equal to minus 1 and 2 for x between minus pi and 0 and 0 to pi. If you want to write it as a Fourier series, the a naught was 1 over 2. The coefficient an was 0. You would get sigma bn. Now, bn is equal to 3 over n pi, 1 minus 1 to the n sine of nx. N goes from 1 to infinity. So that would be the Fourier series for this function. Okay, is there any question here? Okay, is everything clear? Okay. So now let's continue. There are two things I should mention. One is that what if we have a function which has different domain? What if the domain of f is not 2 pi? So we can correct everything with a change of variable. So if the domain, so if the period of f is equal to 2 pi, the Fourier series of f would be a naught plus sigma an cosine of nx plus bn sine of nx. Whereas we saw a naught was 1 over 2 pi integral from minus pi to pi fx dx. An is equal to 1 over pi integral from minus pi to pi fx cosine of nx dx. And bn, the similar thing with sine. Same thing, rather than cosine, we would have sine. Now, what if the period of f is not 2 pi, but it's 2 times some a? So here a plays the role of pi, or well, pi plays the role of a. I still write down the period as 2a. It's for convenience, actually. So the form of Fourier series would be slightly different, still very similar. It would be still of the form a naught plus sigma an. Rather than cosine of nx, we would have n pi over ax plus sigma bn sine of n pi over ax, where a is the half of the period of the function. And then also these variables, they have similar definitions. Rather than 2 pi, we have 2a. Rather than minus pi to pi, we have minus a to a fx dx. And then an is, rather than 1 over pi, it's 1 over a integral from minus a to a fx. Rather than cosine of nx, it would be n pi over ax dx. So for example, if a was pi, as you can see, the pi in numerator and denominator, they would cancel each other and we would get the previous thing, right? Which there was no coefficient inside, but n. And bn is similarly 1 over a integral from minus a to a fx sine of n pi over ax dx. And everything would be similar. Okay. So let's do an example about this thing. This is an example from the book. Find the Fourier series of y equals absolute value of sine of pi x. Okay, think about this one for a few minutes. Okay, so the first step is to find the period of the function we have here. So here our function f of x is equal to absolute value of sine of pi x. And we should see what is the period of this function. So one simple way is to first consider it without the absolute value. So we would have sine of pi x. The period would be 2 pi over pi, which is 2. But if you remember, I told you when we have the absolute value, we should actually divide the period by 2. So the period of this function f is actually 1. Okay. So going back to our previous convention, we were showing period with 2a. So 2a is equal to 1, which means a in our previous computations is equal to 1 over 2. This function, the absolute value of sine of pi x, it is positive when x is between 0 and, well, when it's between 0 and 1 over 2, sine goes from 0 to sine of pi over 2, which is 1. And that is positive. So we would have sine of pi x here. When x is less than 0 to minus 1 over 2, sine goes from 0 to minus 1, and that's non-positive. That's actually when x is less than 0, it is negative. So the value of absolute, so the absolute value would be actually the minus sine of pi x, right? So having that in mind, we can now start computing. We can start to compute a naught, an, and bn. So now we can compute a naught, an, and bn. Let's start with a naught, a0. What was the definition of a naught? It was 1 over 2a integral from minus a to a fx cosine of n pi over ax dx. Here a is 1 over 2, so it would be equal to 1 over 1, which is just 1, integral from minus 1 over 2 to 1 over 2, f of x cosine of n pi over n, which, sorry, we are computing a naught. I'm writing the formula for an. So there is no cosine, sorry. So we would have integral of fx dx. Now, again, fx, we can, well, it's sometimes positive, it's sometimes sine of pi x is negative. So because we have absolute value, again, we can break it into two integrals. So we can break it to an integral from minus 1 over 2 to 0. On that interval, the value of f is minus sine of pi x. And then there would be another part, which is integral from 0 to 1 over 2. And on that interval, f is equal to sine of pi x dx. Now, the first integral is equal to cosine of pi x over pi. We should evaluate that on minus 1 over 2 and 0. The second integral is equal to minus cosine of pi x over pi. You should evaluate that from 0 to 1 over 2. Now, cosine of 0 is 1, and cosine of, so we would get 1 over pi, and cosine of pi over 2 is 0. So from the first term, we just have 1 over pi. From the second term, we would have cosine of pi over 2 over pi, which is 0, and then we would have cosine of 0 over pi, which is just 1. And so we would get 0 minus 1 over pi, which the sum would be 2 over pi. So the value of A naught is simply 2 over pi. Okay, so that's the constant term. The next step would be to compute AN, right? AN is equal to 1 over A integral from minus A to A fx cosine of pi x n pi over A x dx. Again here, because A is 1 over 2, 1 over A would be 2, integral from minus 1 over 2 to 1 over 2 fx times cosine of 2 n pi x dx. Again, we can break this integral into two integrals. So it would be 2 times integral from minus 1 over 2 to 0. And f of x on that integral is minus sine of pi x cosine of 2n pi x dx. And then we would have an integral from 0 to 1 over 2. On that integral, f of x is sine of pi x. Then we would have sine of pi x cosine of 2n pi x dx. So we should compute each integral. I mean, we did similar things. So I would just write down the final value, the final result. So these integrals, actually, they're not hard to compute. So I'm assuming you can do it if you spend a little time. So the final answer is minus 4 over pi times 1 over 4n squared minus 1. So AN would be this number for any n, minus 4 over pi, 1 over 4n squared minus 1. That would be AN. Now, what is BN? Well, BN is equal to 1 over A integral from minus A to A, f of x, which here is absolute value of sine of pi x, sine of 2 pi n x dx. Now, let's look at this thing. Let's see if we can kind of guess what is the answer here. So if I replace x with minus x, this part here does not change because, well, because sine of pi minus x is equal to minus sine of pi x. But after the absolute value, it really does not matter. It is equal to sine of absolute value of sine of pi x. So it does not affect this one if I replace x with minus x. If I replace x with minus x here, actually the negative sign would come out of the function because this is an odd function. So the first one is an even function and the second one is an odd function. And the multiplication of an odd function and an even function is an odd function. And when you are taking integral of an odd function on a symmetric interval around 0, The integral again would be 0 because the positive side and the negative side would cancel each other. So this integral is 0, so the numbers Bn are equal to 0. So the Fourier series of sine of pi x, the Fourier series, would be equal to the constant we computed, 2 over pi plus sigma some numbers times cosine of 2n pi x. What are those numbers? Well, they are equal to minus 4 over pi, 1 over 4n squared minus 1. So that would be the Fourier series for this function. Is there any question? And well, they are actually equal. The important thing here is that we have the equality. Okay. Okay, great. So another point I wanted to mention is that sometimes a function is not defined everywhere, or it's not periodic. What we can do is we can kind of take some part of the function and extend it so it becomes a periodic function. Okay, so for example, if we have a function defined, suppose we have a function f defined on an interval minus a to a, we can just, whatever it is, we can just repeat that. The resulting function, in a way, so we would get a periodic function. The resulting function, maybe it might not be continuous, but it's okay. We, in our computations, as we will see, we really don't care about this type of discontinuity. So here we would have a jump. This is the kind of discontinuity we have. This is not something we would really care about at this point. So if we have a function defined on an interval, if we extend it so it becomes periodic, let's, in this course, we show it with f bar. It's called the periodic extension of f. Okay, so if we want to know value of f at any point, we can just bring it back. If the inner, so here the period is 2a, we can, for example, we want to see the value of f bar at x, we can subtract some multiple of 2a, some integer multiple of 2a, until the point comes into this interval. And then we know the value of the function at that point. So it would be equal to f of the function at that point. This is one type that we can extend the function. There is another way. So for example, if we have a function only defined from, say, 0 to a, there are two different types we can extend this function. So suppose we have a function like this, f. One type we can extend it is called even extension. So we can just suppose y, we can think about y as a mirror, the y-axis, and reflect it with respect to y. We get something, and then we can just, then we can kind of look at the periodic extension of the result. So we would start with this red function, and then we would reflect it, and then we can just repeat the same thing. That's one idea. The other idea is that if they give us the same function, f, well, again, let me show it with something red. We can look at something called odd extension. We can define, so for negative values of f, we can just reflect the graph of the function with respect to the origin. So we would get something like this, right? And then then repeat that periodically. So the function would look like this. So looking at very simple examples, suppose f of x is equal to x for x between 0 and 1. So f of x is like this. The even extension of f would be like this. Look at this function, right? And then repeat that. Look at the periodic extension of that. That would be the even one. The odd extension of f, so if this is f of x is equal to x, the odd extension means just extend the function like this, reflecting it with respect to the origin, and then take the periodic extension, then repeat that result. These two kinds of extensions are quite important to us, and we will see how it plays a role in the theory of Fourier series. Now, to see how even functions and odd functions play a role in Fourier series, the point is that if a function f is even, when we look at the Fourier series of f, it has a naught plus. There would be a sum sigma an cosine of, say, n pi over ax. There wouldn't be any sine part. Just like we saw in the previous example, when f is even, the integrals for bn, all of them will become 0. And if f is an odd function, the Fourier series of f wouldn't have actually the cosine part. It would have only the sine part. So that's one important property of these functions. Okay, I do not want to start a new topic. Let me just talk about it a little bit so we would get ready for that. So we started with a function f, and we wrote a Fourier series for that. So Fourier series is an infinite sum. So what is the hope? What are we looking for here? Are we claiming that f is equal to that thing we are writing? Is it correct? Is it possible? Is it true for any function f? Well, the answer is no. This is not correct for any function f, and it's not true at any point x. So you see, we can think about the space of functions as a vector space. We can think about this as a vector space. You see, when we have two functions, we can add them, we can multiply a function by a scalar, by a real number. So here, what we are doing is kind of like we are thinking about, in some sense, we are thinking about cosine and sine of nx, these functions, and here 1, so 1 cosine of nx for every n into natural n, the sine of nx. It seems we are thinking about these functions as a basis for the space of functions. Although this basis is not a finite basis, it has infinitely many elements. But if we think about the space of functions as a vector space, and if we think about these functions as a basis, we kind of can think to write any function as a linear combination of the elements of the basis. And that's kind of what we are doing. But another way we can think about this is rather thinking about these sums from 1 to infinity. We can think about these sums from 1 to some n. So let's call that Fn of x. And one practical question one can ask is that, does Fn, does it converge to f when n goes to infinity or not? So the question is that, does this sum, as we like raise n, does it get closer and closer to the function f? So there are a few tricky stuff here. During the next session, we might look at some examples. I hope I can use some software to show you how the right-hand side would converge to the function f. As we increase n, we can look at the graph and see it's getting closer. But one tricky question is that, what do we mean by convergence? So when we have a sequence of points in R, for example, the concept of convergence is really trivial. It makes sense. But what does it mean for a sequence of functions to converge to another function? What do we mean by that? And the answer, there is no unique answer. There are different ways of convergence. There are different definitions for a sequence of functions converging to another one. There is pointwise convergence, there is uniform convergence, and there are more complicated convergence. They're related to Sobolev spaces, usually called LP convergence or WKP convergence or other things. So for functions, it's not as trivial as just sequence of points converging to another point. So I would just define the two very basic types of convergence, and we would see if Fourier series, if it converges in these two forms or not. We would see that in the next session. But we would say a sequence of functions Fn, suppose all of them are defined from some interval to R. We would say they converge, this sequence converges to f. Let's say f is also defined on the same sequence. If for any point x in the interval, if I look at Fn of that point, now this is going to be a sequence of points, right? Fn of x. This is a number. This is not a function anymore. This sequence of numbers converges to f of x as n goes to infinity. So in another sense, I'm saying a sequence of functions converges to another function if at each point, if I evaluate those functions at that point, the sequence converges to the function f at that point. This type of convergence is called pointwise convergence. This is kind of, in some sense, the most basic type of convergence. So one example you can look is, suppose Fn of x is equal to the x to the n. And suppose we are defining it on the interval from 0 to 1 to R. So the first element of this sequence is the function x. The second element is x squared, x cubed, etc. So if we look at the graph of these functions, the first function is like this. The second function is like this. The third function is like this. X to the 4 is like this, etc. Pointwise, the limit of these functions, x to the n from 0 to 1 to r, is function f of x equal to 0 if x is between 0 and 1, but not equal to 1, and it is equal to 1 if x is equal to 1. So the limit of these functions, just on this interval, right? The limit of these functions, x squared, this is x squared, the next one is x cubed, the next one is x to the 4, the next one is x to the 5. Their limit is this thing. It's everywhere 0, but at this point it becomes 1. And intuitively, if n is very, very large, x to the n is kind of like this. And as n grows larger and larger, the function becomes closer and closer to the 0. But the value of x to the n is equal to 1 when x is equal to 1. Doesn't matter what n is, and for any natural number n. So this is an interesting phenomenon because we have a sequence of continuous functions. All of them are continuous, but the limit is not, is a discontinuous function. So we have a sequence of functions converging to a discontinuous function.